in order to answer the question whether this is a possible path and a possible parameterized representation of the motion of a particle around the sun, we ask, well, is it true that r squared d theta dt is constant, that this vector sweeps out equal areas in equal times? There are a number of ways to answer this question, but we'll just go with the most direct. Let's write r squared d theta dt. Let's write that expression out and see if it's constant. Okay, now r of t is just the square root, so that if we just write the contents of that square root, the argument of the square root down, then we're going to get r squared of t. And d theta dt is the t derivative of this angle. Now there are a couple of finer points about this angle. The arctangent, of course, gives us only angles between negative 90 and plus 90 degrees, or between negative pi over 2 and pi over 2 radians. We're not going to worry about that for the moment. Let's just see if we can answer the question without having to worry about that. Okay, so we have r squared d theta dt then equals this expression. We're going to have to take the derivative of this mess. Well, let's see now. What's the derivative with respect to t of this arctangent? First of all, well, let's just write it down. Derivative with respect to t I'm writing a partial derivative sign, but there's only one variable. So the derivative with respect to t of this expression equals what? Well, the derivative of the arctangent of t with respect to t would be 1 over 1 plus t squared. Unfortunately, this isn't just the arctangent of t, it's the arctangent of another function of t. I'm going to call this function g of t, and then I'm going to say that by the chain rule, the derivative with respect to t of this is just 1 over 1 plus g squared of t times, let's do it with the d dt notation, dg of t dt, where our g of function is 5/3 tangent of omega t. So we're going to have 1 over 1 plus 25/9 the square 5/3 times the square of the tangent of omega t. That's going to occur here, but we've also got to have the derivative with respect to t of our g of t function. So what's dg dt? Well, let's try that. dg dt is the derivative with respect to t of 5/3 tangent of omega t. Now, we can write that as the derivative with respect to t of 5/3 h of t and that's going to equal what? It's going to equal 5/3 h of t prime. I'm going to use the prime instead of the d dt notation for this. That's the derivative of the inner function. And that's going to be 5/3 h prime of t, which is 5/3 times the derivative of tangent omega t. And the derivative of the tangent is the secant squared, so this is going to be 5/3 times the secant squared of omega t, and is going to be 5 omega over 3 times the secant squared of omega t. Okay, well, that's getting a little messy. One thing that we can probably see is that there's almost no hope that when we put all this together into a single derivative and multiply it by 9 cosine squared of omega t plus 25 sine squared of omega t, it's going to end up being constant. This means that this could not be the path of a planet moving about the sun. Now recall that r squared d theta dt was this expression times this derivative. This derivative is 1 over 1 plus g squared of t times dg dt, where g of t is 5/3 times the tangent of omega t. And the derivative with respect to t of 5/3 tangent omega t, we didn't really need to use the h of t here. It's fairly straightforward to take this derivative, knowing that the derivative of the tangent is the square of the secant. The inner function is omega t, and we end up with 5 omega over 3 secant squared of omega t. And we put that together into our expression for d theta dt. We get this, so that r squared d theta dt is 9 cosine squared of omega t plus 25 sine squared of omega t multiplied by all this mess. And we can do a little simplification as we go through. We can multiply numerator and denominator here by 9/25, which will then multiply the 5/3 to give us 3/5, and we're going to end up with omega secant squared of omega t over 25/9 plus the tangent squared of omega t, and it'll be 3/5 of this. Now that's a fairly complicated expression. We could play around with the sines and cosines and attempt to simplify this, but we could take 9 of the sine squareds and match it with 9 of the cosine squareds and just get 9. The secant squared, well, the tangent squared is the sine squared divided by the cosine squared, which is the sine squared times the secant squared. So we might be able to do something with that, but as it turns out, it's not too difficult to show that this is anything but constant. This is not constant. And we could go on, but it would just be an exercise in algebra and differentiation and so forth. But it turns out that, again, the situation is, the question is whether this can be a parameterization of something in orbit around a planet at the center, and the answer turns out to be, since r squared d theta dt is pretty clearly not constant, no, it can't be. Now we have a more direct way to get a handle on this situation.